Is it possible for distant galaxies to be moving away from us faster than the speed of light? And if it is, would it be possible for us to see them? Surprisingly, the answer to both questions is a resounding yes. How is that possible? How can something travel faster than the speed of light? Today we will try and paint an accurate picture of the universe based on the lambda cold dark matter model, which is the best cosmological model today. Once we have painted that picture, the answers to our questions will be straightforward. Let's assert that some kind of space-time quantum foam sort of something existed before our own universe began, before our Big Bang. Then we simply let Heisenberg's uncertainty principle go to work for us. If we look at the tiniest speck allowed by quantum mechanics, a small volume with a Planck length as its linear scale, the speck would have a volume of 10 to the minus 99 cubic centimeters. And the largest amount of mass or energy that we could put in this volume without it becoming its own black hole is about 1/100,000th of a gram. Interestingly, the uncertainty principle allows this much stuff to be created out of nothing for as long as 10 to the minus 43 seconds. Not a very long time, but it will prove to be enough. Because if that much energy is created in the form of a certain type of scalar field, then we have just successfully created a universe. The best model of how our early universe grew after that initial quantum fluctuation created it includes inflation, a period when the scalar field divides space into a brief period of extreme exponential expansion. During inflation, space erupted from its tiny beginnings into an unknowably huge volume. This enormous expansion generated an enormous amount of gravitational binding energy, at least 10 to the 85th grams. And this was counterbalanced by a corresponding group of positive energy in the scalar field. What began as a mere fraction of a gram of energy has now become 10 to the 85th grams. This is a huge number, large enough to account for all the matter and energy that exists today. But notice that the total energy in the universe is within a quantum fluctuation of equaling 0. As a byproduct of the enormous growth of space during the inflationary period, tiny quantum fluctuations grew into macroscopic fluctuations in the density of the scalar field, making it ever so slightly lumpy. This lumpiness provided the seeds for the formation of stars and galaxies and all the structure we see in the universe. At the end of inflation, the temperature throughout all of space was still enormously hot. But as space continued to expand, it cooled, and the energy of the scalar field, which now filled all the new and enormously huge volume of space, decayed into dark matter and dark energy and normal matter. The photons and quarks and electrons, which in turn settle down into the protons, neutrons, and atoms that populate the universe today. After about 380,000 years of expansion and cooling, charged particles got together to form neutral atoms. And suddenly the photons that were bumping into charged particles every second or two were free to zip unhindered across space. This is the origin of the cosmic microwave background that we see today.